Hi, welcome to R2E. So in the last two videos on our quantum mechanics 2 series, we talked about perturbation theory, and we talked about formalism of perturbation theory, and now we're going to talk about a few examples on perturbation theory. Okay, so we're going to talk about just a second. Yes, so now we're going to talk about examples of perturbation theory. And the first one we're going to discuss is this harmonic oscillator kind of problem. So I have this Hamiltonian. Okay, let me just move the hats. I just don't want to have a hassle of hats. So that is p square upon 2m plus 1 by 2 m omega squared x squared. So up to this point, this problem is exactly solvable. And now I will add here add a perturbative term, that is epsilon by 2 m omega squared x squared. Now it's not that this problem is now entirely non-analytical. You can't solve this problem. Actually, you can still easily figure it out. So this is h, and you can still write p square upon 2m plus 1 by 2 m. There is omega squared 1 plus epsilon x squared. So exactly, so all what has happened is your omega has gone from omega to square root 1 plus epsilon omega, right? So all this is all what has happened here. Now let's look at the new perturbed eigenkets and the eigenenergies using perturbation theory. Okay, so we had our delta and okay, so delta n is equals to v n n plus some, okay, this is lambda, this is lambda squared, k not equal to n, v k n squared divided by en 0 minus of ek. Yes, I'm sorry, 0. Great. So this is the correction to the energy, and similarly the correction to the energy, so the eigenstate it will be n0 plus lambda so this is the correction up to first order. Okay, so now what we'll be interested in calculating is, and obviously there are higher order terms, sorry, this is not lambda, this is lambda squared. Okay, so obviously what we are interested in is calculating the perturbative effect up to second order because of this last term that we have introduced, which have changed the frequency of the Hamiltonian in principle. And yeah, now we want to see it. So okay, let's compute the first of all the energy shift up to first order. So let me write this. For first order effect, so we have to compute this, and obviously we just want to compute it for the ground state. We don't want to go higher because this index n here, it means you can compute it for any energy level. So in principle you have infinite energy levels, you can compute the corrections for all of them. We don't want to do that right now, we just want to get it for the ground state. Okay, Seems fair. Okay, so if we want E of 0, that is up to first order, so it should be nothing but expectation value of the perturbation, so which is epsilon by 2 m omega squared 0 x hat squared 0. Now we will use the A's and A daggers. So we know that x hat is square root h bar upon 2m omega A dagger plus A. So I'm going to plug that in, and then I will have okay, let me, so I will have here h bar 2m omega, and then I will have an A dagger squared plus A squared plus A dagger plus A dagger A. Alright, so this term out here be outright 0, this will be 0. Now this is here in a normal ordered form, so this will also be 0. For those who don't know what is a normal ordered form, what is a, let me use a different pen. What is a normal ordered form? Is one in which all A daggers are on left and all A's are on right. Okay, it makes sense. So something like A dagger square A square, it's a normal ordered form, but A squared A dagger square, it's not a normal ordered form. Okay, fair enough. So now we have h bar upon 2m omega. You want this expectation value, and this will be h bar upon 2m omega 0 1 plus A dagger A 0, and this will be h bar upon 2m omega. Great. So so this is the expectation value. Now if we multiply this with the next prefactor, that is epsilon by 2 m omega squared h bar upon 2 omega omega cancel, m cancel, so we have epsilon upon h bar omega by 4. So this is the correction to the ground state energy. Good, this is great. Now okay, so let's also calculate the correction, the second order correction, right? So to compute a second order correction, so I also want to compute a second order correction to energy, right? So in principle, I'm supposed to compute this matrix element, that your k is not equal to 0, and you are supposed to compute this matrix element. This is so your k 0, this has to be whole squared, and e0 0 minus of e0 k, right? You are supposed to calculate this. So okay, let's take a look at it, right? So vk0 in principle is, you have your prefactor, so that will be your epsilon. Okay, so that will be just be h bar omega by 2, I believe, because rest of everything will come out of the expectation value. And so you have your k, and then you have your not exactly x squared, well yes, x squared, but we just only consist of the operators, right? So I have taken out the prefactor that it have, and I have done everything that has to be done, and now I have this h bar omega by 2, and this x square only consists of the operators, so this will be epsilon h bar omega by 2. So because it's k, so I can in principle write it as 0 a to the power k upon square root k factorial, and this will give you a, so okay, this part right out here will give you a bra k, right, and here you will have a dagger squared plus a squared plus a dagger plus a dagger a, and again there is get 0, right. So let's look, write it in its full glory. So that will be 0 ak a dagger squared upon square root of k factorial 0 plus, this has to be equal to, great, and this will be 0, this will be ak a squared upon square root of k factorial plus 0 ak a dagger upon square root of k factorial, this is again 0, and this is 0 ak a dagger a 0 upon square root of k factorial. Great. Now here is a thumb rule, not a thumb rule, you can verify it. In principle you can, I hope one can prove it using some techniques from induction, mathematical induction, but I'm not sure about it, how do one do that, but I am not, or nor I'm going to, nor I have thought about it, or nor I'm going to put the proof or here right out after checking it. So the thumb rule is the only terms that will give a non-zero contribution should have equal number of a dagger and a. Okay, so they should have equal number of a dagger and a. That's how you will get a non-zero contribution here, otherwise you won't. One can check it. So let's look at these terms again. So here, for us to have a non-zero contribution, the k has to be 2. Here it cannot be because it only have a dagger terms, so this will always be 0. Here, so there is one a dagger, so there need to be only one a, so obviously this is 0. So the k has to be 0 here, and here also k has to be 0. So only then you could have a non-zero contribution, but here, because again it is normally ordered, it will always be 0, so doesn't matter at all. So okay, so so in principle we could have a non-zero matrix element, so we could have vk0 to be non-zero only if either k equal to 0 or k equal to 2. These are the only two ways in which you could have these you could have a finite matrix element, right? Otherwise you won't have a finite matrix element because of the thumb rule I have just written up here, and this thumb rule works. People who might be doing quantum field theory, this thumb rule will be a lifesaver when you will be doing Feynman diagrams or using Wick's theorem and all. Okay, I think this is Wick's theorem. I don't remember it clearly, but anyways. Okay, so I have already computed a v00. Now let me compute. So let me compute v20. So that is epsilon h bar omega by 2. And now I have this obviously, so only because now I'm talking about 2, so only this matrix element will be there. So let's see. Mm, this is 0, and obviously there was a square root of 2 factorial, so let me just write it as 2 outside here. And then there is a dagger 0, and this is epsilon of h bar omega upon 2 upon square root 2. So obviously, it's very simple. There is a very simple rule, but I'm not going to tell it because I haven't verified it, or nor I remember it clearly, that you have to check like how many times a have to cross over to give you a number that will be the number here that need to be multiplied. So that is the expectation value of this crazy operator. But for us, for right now, we will do the whole exercise of calculating this whole operator. Okay, how do we do that? So the idea is quite simple. You have to make it normal ordered. So let's just start off with, right, so this is 0, a a a dagger 0. So first it will be a, so I'm dropping off the zeros, so that will be a 1 plus a dagger a, and there is a dagger, so it will be a dagger plus a dagger a dagger. Now I'm going to do one more. So this is a dagger. Okay, I have to write it normal ordered, so just let me do it here. Then it has to be 1 plus a dagger a, and the first term also has to be shifted, so it has to be 1 plus a dagger a dagger. So this will be 1 plus a dagger a plus a dagger plus a dagger a dagger. And now this is 1, so this will be 2 plus 2 times a dagger a, clearly yes, and the last term will give you a dagger a 1 plus a dagger a. So there is 2, this 2 plus 3 a dagger a plus a dagger a dagger a. Now you have to do one more shift, and that will give you 2 plus 3 a dagger a plus a dagger a plus 1 a dagger. So that will give you simply 2 plus 4 a dagger a plus a dagger a, right? Quite simple. But now last two are in normal order, so if you take the expectation value, so they will 0 and only 2 will be left here, so you have to just multiply by 2 right up there. So I think v20 would be nothing but epsilon h bar omega by 2 square root 2 multiplied by 2, I believe. I hope I haven't made a mistake, which I think I'm making something. I'm making some sort of a mistake, I believe, here, and right now I'm not quite sure of what it is. Interesting. Okay, let me recheck. Let me recheck if I have made a mistake here. Hmm. Oh yes, I made a mistake. I knew I made a mistake. So it doesn't has to be 2. In principle, it has to be a 4 here. Okay, because you have a 2 coming out from here, 2 coming from the square part, and yes, this has to be 4. And yes, okay, so this has to be 4 again, 4 again, and yes, so this is 4, and now this is epsilon h bar omega upon square root 2. Great, makes sense, right? So now so we got the first order correction, obviously, and so for the second order correction, what we got is so your second order correction is in principle has to be the square of it, so it has to be h bar squared omega squared upon 2, and it has to be multiplied by the energy difference between the two states. So the ground state energy is 0, and so I'm skipping the half, and is 2 h bar omega, so that is minus of h omega by 4. So this is the second order, whatever you call it, the energy, second order effect. So I think that's not a problem here. Okay, I believe it is correct. I think so. No, I don't think so. I'm sorry, I again missed a 2 here. So there is a 2 here. I'm sorry about all these silly mistakes. So there is 2 and there is 4. So there will be into 4, and that will be minus of h bar omega by 16. Great. Yes, now everything is fixed. So this is the second order shift that we had, and now we want to look at one more thing, that is yes, so correction to the eigensets. So correction to the eigensets, let me put a heading here, correction to the eigensets, right? So you have your, so I'm just going to do correction to ground state energy. So this is ground state, so get n 0, so this has to be ground state plus k not equal to 0 v k 0 mod upon e 0, and this has to be 0 minus of e 0 of kth level. Now as I told, the only and there has to be k0, and as I told earlier, the only relevant energy, or sorry, the only relevant level out there in this summation is level 2. So this will be get 0 plus vk0 was epsilon h bar omega upon 2 square root 2, and this part right out here was minus of 1 upon 2 h bar omega, I believe, yes, and that is obviously unperturbed second level. So your this correction, or whatever you call is the dressing, or whatever you like to call it, is minus of epsilon upon 4 square root 2 to 0. Okay, so there is mixing with the second level, right, which is great. Okay, but as I told earlier, we can also in principle exactly solve this on this this Hamiltonian up here, right? We can also exactly solve this Hamiltonian, and let's take a look after what happens if I exactly solve this. Okay, so but because there is not much has to be done, so I know that the energy of the Hamiltonian is h bar omega n plus 1 by 2, and here this simple it is quite simple because omega is omega 1 plus epsilon to power 1 by 2 n plus 1 by 2, and so this is h bar omega, so that will be 1 plus uh, epsilon by 2, there is minus of epsilon square by 8, and there is n plus 1 by 2. Okay, so this is h bar omega n plus 1 by 2 plus epsilon by 2 h bar omega n plus 1 by 2, and there is minus of epsilon square by 8 h bar omega n plus 1 by 2. Okay, so if you plug n equal to 0, you would get the same energy contribution as we discussed, I think here. Yes, here you will still get a energy contribution of h omega by 4, which is great. And we also got an energy contribution at second order, which we haven't calculated or nor we want to. Oh, we have actually, I think. Have we? I think we have, right? Oh yes, we did. Yes, so that was h bar omega by 16 with a negative sign, and again here this is h bar omega by 16 with a negative sign. So clearly, so the perturbation is working in different orders, which is good, great sign. That means we did the calculation right. That is proof of that. But in principle, if I assume that my calculation was right, and so this is the proof of concept that you can, this is a proof of concept, and one should take this quite seriously or take it as a message that um, by doing perturbation, in principle you are getting closer and closer to your real solution. So here we have a problem which is exactly solvable, and we are also doing perturbation theory on the same problem, and we are realizing that as we are going higher and higher in perturbation, we are actually getting closer and closer to the solution to the problem, which in our case is known to us, so we can directly compare us, but in most of the problems will be unknown. We won't know what that solution is, but it's an example that shows that yes, by doing perturbation you can get closer and closer to the real solution. Okay, great. Now obviously we would also like to find correction to the ground state. So our ground state wave function psi 0 of x is given as square root of wait, so yep, so I think it is given as m omega upon pi h bar to power 1 by 4 exponential of minus of m omega x squared upon 2 h bar. Now obviously omega goes to square root 1 plus epsilon omega, so that means omega 0 of x is m pi upon h bar to power 1 by 4, and that is 1 plus epsilon to power 1 by 8, and there is obviously omega to power 1 by 4. So this is one thing, and in the exponential we have m square root of 1 m omega x squared upon 2 h bar, and then we have square root of 1 plus epsilon, So let me fix this. So that will be m omega upon pi h bar to power 1 by 4, and that will be 1 plus 1 by 8 epsilon plus higher order terms, and then there is exponential of m omega x square upon 2 h bar, so that is 1 plus 1 by 2 epsilon again. So let's again fix this. So that will be okay, so let's, okay, no worries. Okay, so that will be m omega pi upon h bar 1 by 4, 1 plus 1 by 8 epsilon. There is exponential minus of m omega x square upon 2 h bar, and there is also minus of epsilon upon 4 h bar. So this is good. Now, okay, now again I have to use this, and I have to do the Taylor expansion for this, and that will be m omega pi h bar to power 1 by 4, 1 plus epsilon by 8, and this is e to the power minus m omega x square upon 2 h bar, and then we have 1 minus m omega x square, obviously epsilon here, and 4 h bar. Great. So let's get the terms first order in epsilon, and we will leave the terms of epsilon squared. So first we always have our wave function back, anyways, which is good. And then we have epsilon by 8. Okay, so let me take epsilon here, and then we have 1 by 8 m omega pi h bar power 1 by 4 e to the power minus omega x square upon 2 h bar. So this is good. And obviously we have a product term here, and okay, wait, so we should have a minus of m omega x square upon 4 h bar, m omega upon pi h bar to power 1 by 4, exponential of minus of m omega x square upon 2 h bar. And if you realize it, so so just to write it as, the first is the 0th order Hermite polynomial, the second one is epsilon 1 by 8 minus of m omega x squared upon 4 h bar, and the second is again a 0th order polynomial, Hermite polynomial, not 0th order actually. So and this is not okay, so this is not exactly in x, it's in some x by x 0 that you have to fix the dimension here, and then there is exponential minus of m omega x square upon 2 h bar. Okay, so this looks like, actually this is an x square, so this is like a some sort of a, this could be written as some sort of a second order Hermite polynomial upon x naught, and which kind of shows what we have shown above here, that the first order correction is actually the ground state plus the second unperturbed state. So yes, so with this we have explicitly solved the problem of perturbed harmonic oscillator with an additional perturbation term, which is also harmonic oscillator type, but all it does is just shift the frequency. It is exactly solvable. We compared the two solutions, one using perturbation theory and one using exactly solving the problem, and we realized that yes, they both are same. So yes, so this was the power of perturbation theory, and probably in the coming up examples we will solve problems which are not exactly solvable, but we will using the perturbation theory to get some good nice insight into the problems. Okay, thank you, see you in the next video.